So this talk is about vision and sound together, and specifically those two things coming together to allow us to reason about spatial things in 3D environments. So that's the theme of everything I want to show you today. This talk is meant to be somewhat high level so that I can kind of cover more ground around things we're doing here, and I would point you to papers for details or discussion offline. So the motivation for the work we're doing here is coming strongly from this idea that we need to link perception with action. So it's one thing to have computer vision that is understanding the visual world kind of from a distance, and it's another thing to have perception that's understanding the visual world in the very context of an agent that is trying to act in it. And this includes agents, of course, like mobile and autonomous robots. It also includes agents and problems in augmented reality, where we have a first-person experience of the world from human eyes. So we're considering this broad space of problems and trying to push our computer vision work in the direction that will support acting agents. And in particular, I want to start with the case of navigating agents. So if we have an agent that can see the world from an egocentric view, like shown in the top left, then we want them to be able to enter a new space, an unmapped one, suppose this 3D environment, and still do intelligent things within it, even though the environment's not yet mapped. So in other words, to the agent, the space is yet to be understood, but we'd like agents that are smart about using what they see in their first-person perspective to both map the space and solve a goal, like navigating to a particular place in the environment. And there's a lot of great work happening in this space, certainly lots of rich work over the years from robotics and increasingly attention from the core computer vision community trying to bring together the perception towards the action of such a navigating agent. And this work has been furthered by the availability of highly realistic 3D simulators where you can get visual simulations or even reconstructions from real-world environments in order to both train and evaluate agents that are moving in these new spaces. So what this does is allow you to train systems, often deep reinforcement learning systems, to encounter new spaces and make intelligent motions within them. Now, that said, what's been limiting, we think, so far is that these environments have been purely visual. So they're silent, and the agents have been purely visual agents, so they're deaf. And so the first thing I want to show you is how we can think about enhancing these environments, particularly even in simulation platforms that allow these reproducible kind of experiments to further have the audio modality. But firstly, what happens once we have the ability to hear in 3D spaces? What will it help our agents do? So sound can inform us about a target location. So the phone's ringing in some other room. Our agent should hear it and be able to move to that space. Sound will inform us about activity. So the events that are happening will have associated sounds with them that we'd like to understand. Sounds can also inform about semantics. So just as we might know what a faucet with water looks like, if we hear it, that sound is also a signature and can be suggestive even before we see it. And finally, sound is going to give us direct information about the geometry of the space, where are the major surfaces, and what are their materials. Okay, so sound seems very relevant to all of these problems that could be joined, in which sound could be joined with the visual sensing to do intelligent things. And so this talk is going to touch on examples from our work that's trying to capitalize on just those properties. So let's then talk about what makes sound so rich for spatial sensing together with vision. So there's two sides of this equation. On the one side, you have the environment itself that's going to affect the sounds we receive. And that's because the geometry of the space, the big walls, the big furniture, the materials that those objects are made of, as well as where we are in the environment versus where a sound source is in the environment. All of these are going to affect the sounds that we would receive and be telling about those properties of geometry material. Now, the other side of the equation is the agent itself. And so an agent's spatial sensing through sound is affected by the placement of the source in the environment, but also the agent's own body. So as you can see here, we agents and agents we might build can have multiple microphones. We have our two ears, and the delay in which we receive sound from either ear, or the level difference that we receive it at either ear, these are factors that are going to influence our 3D understanding of the placement of the source, as is even the shape of the ear and how sound reflects against the outer ear shapes. Okay, so we have the environment itself. It's going to influence the sounds and tell us something about its shape. We have the body itself. It's going to influence how those sounds are received. And those two come together to enable spatial sensing with audio. So then finally, let me tell you about our first contribution here in this space that will kind of serve as a platform for the work I'm going to show you in the following. And this is an environment for realistic acoustic sound simulation on top of existing visually realistic 3D environments. So I've kind of referred to those generally so far. Here's an example, this one from Replica. So we've looked at both the Matterport 3D environments and the Replica environments, which are real-world scanned environments for which you can arbitrarily pose a camera and grab an egocentric view for your agent. And what we've done is to supply accompanying sound renderings for those environments. And they're acoustically realistic, using state-of-the-art methods with bidirectional ray tracing for the sound to simulate binaural sound at an arbitrary position for an arbitrary sound waveform of your choice. Okay, so we've pre-computed these. In fact, we've done it for all the yellow dot positions you see here for both every pair of possible agent positions and sound source positions. So you as a user using this public resource that we've created called Sound Spaces can render sounds of your choosing for agents at positions of your choosing. So for example, maybe you want to insert the sound of a phone ringing and it happens right here. Then you can place a camera and microphone anywhere else in this environment and receive the proper vision input as well as the proper sound input. Okay, and this can all be done in real time. So this Sound Spaces platform, let me next show you an example of it working that will give you a sense of the realism of the sound as well as the realism of these Matterport environments in this case. And so on the left, it'll be an egocentric view, and on the right, it'll be a top-down map view of this environment, showing you where the agent's moving. And you won't hear the full binaural sound without going to our website, but here at least I hope you'll hear differences in the level and intensity of sound as the agent moves around. So here we go. And please let me know if you're not hearing the sound through my slide. Okay, so I hope you could hear the sound of the piano playing that got enhanced and would have been more on the left as you passed by it, and then the smoke alarm being very loud as you got close to the kitchen. So that's just a sampling of a path rendered through Sound Spaces with Matterport 3D to get both the sights and sounds for this agent. It also hints at the very first task I wanted to show you from our work using our Sound Spaces platform, and that is audiovisual navigation. So here the target is, where is that ringing smoke alarm, or where is the ringing phone? And the key in this problem setup is that let's keep in mind the agent hasn't already mapped the space. So it's both entering a new home and being asked to solve a navigation task to find this object. Now on the right, a cartoon of why this should be a task enhanced by the audio signal. So if our agent's out here, outside of these rooms, it certainly can't see the phone that's ringing, but it could hear it. And so if it hears it, the sound will be bleeding out of the door of the room in which the object actually exists, as this heat map suggests. And so our agent's job is to be able to learn to use that kind of pattern to set navigation waypoints for itself, or to let it be led to the goal, which is this sounding phone. So the first model that we've developed to try and address this task uses a deep reinforcement learning loop. And so what this means is that the agent will receive observations, which are the pictures, the egocentric view of the environment, as well as the depth in the egocentric view, but also the sound, here encoded as input as 2 spectrograms, those matrices you see here for the left and right ear. So this is the binaural sound that the agent can hear at its current position. And remember, it's spatial sound, so it's going to convey something about not only how far away this sounding object might be, but also at what orientation with respect to the agent. And optionally, we'll have a GPS odometry as input to the agent. Now, in this reinforcement learning loop, then, we're going to train a policy that will choose actions at every time step that tell the agent to either move forward, go left, go right. Okay, so once it's made such a choice based on what it's currently seeing and hearing and what it has seen and heard in the past, as captured here by this GRU, then it will receive updated observations from the environment. The environment changes because the agent has moved in it, and now this loop will continue. So every time you've got an agent seeing something new, hearing something new, deciding how to move, and then getting feedback as a result. Now during training, the way the agent will get smart moving throughout this space is because it'll be rewarded for efficiently getting to the target. So during training, it'll get a reward every time it's getting closer to the target. It gets a bigger reward when it reaches the target. Okay, so from this process then, what we get is a policy. It's a motion policy that says, given what I'm seeing and hearing, this is how I should move to get to the target. And what I'll show you in just a few slides will also relax this assumption of odometry coming for free and force the agent to rely solely on what it sees and what it hears. All right, so first, how does audio help navigation? And I'm going to show you an example and a summary result. First, a baseline agent. This is an agent trying to solve the point goal task. This is a task a lot of researchers have been studying, where in the visual environment, you see the views and you receive a GPS odometry, but of course you don't have the sound. And here's an example where the agent starts at the blue square and needs to get to the yellow one as the goal. And the shortest path would be what you see in pink. But in this particular episode, the agent failed because it didn't realize to kind of exit the room and get down to this target. And in the point goal task, it actually makes a lot of sense why it would fail here, because there's a strong pressure to go towards the XY position indicated in the point goal specification. So in other words, the agent's being told to get down to that position. So in this case, it bumbled around too long, getting stuck in this room when it needed to exit and go down to the pink path. And that'll play out into success rates for navigation that are kind of moderate. A lot of challenges trying to overcome these more long-term navigation needs to get out of the room and into the correct room. Now, in contrast, once we add audio to our sensing, as I just showed you in the previous slide, then the agent can hear the sound coming in through the doors and make a selection of motions that in an aggregate will allow it to get down to the target below. Okay, so audio, point goal, adding audio to the original sensing indeed helps the success rates for navigation, as you can see in this chart on the right. So that's good. And then we're able to add sound and it improves the navigation ability. And we're also interested in, what kind of features were actually learned by this agent as it paid attention to the sound. And we can start to visualize that here in two t-SNE projections down all the way to 2 dimensions from the learned CNN feature on top of the binaural spectrograms. On the left, they're color-coded by distance to goal at any given point. And on the right, they're color-coded according to angle to goal. And so what's cool here is, if you look, say, on the left, the fact that these colors are clustering together, and the red points are near red points, blues are near blues, this means that the agent is encoding a feature in that high-D CNN feature space that reflects how far it is currently from the goal. And it's essentially reading that out, learning how to read that out from the sound. Similarly, although a little bit less strong of a signal, it's learning to capture the orientation of the goal with respect to the agent, as you can see on the right. Okay, so what does this mean? So in the context of that end-to-end reinforcement learning loop, it's pulling the meaningful signal from the audio that may help navigation. And I'm showing distance and angle to goal. Of course, there's other aspects about the sound that it can use, and that will also be part of the learned features. Okay, so audio helped our agent, who before only could see, now can hear. This is good. Almost to be expected, right? If we add more modalities, surely we should only do better. And so we've established that. But next I want to show a greater challenge for this agent, where instead of having perfect GPS as these agents have so far assumed, where it could keep track of where it is within this environment, we're going to add noise to the GPS. So as you go from the left to right, the GPS sensing is getting worse. Now, what happens to the baseline agent, that point goal agent, is a pretty severe degradation in its ability to navigate. So here, high is good. This is a success rate for navigating. And you'll see that in contrast, the audio-based agent I just showed is relatively stable, even when this noise happens. And why is it possible? Well, just as we saw, even from the audio signal alone, we're getting strong spatial cues. Now, even more exciting, I think, is if we pull away the GPS altogether. So if we train agents that do not receive that third modality of GPS, but just see and hear, then they're, of course, immune to any problems with the GPS odometry, and we'll get this level of stable success rate in navigation. Of course, there can be sound noise as well, and even with relatively severe microphone noise, this agent is going to produce quite close performance in terms of navigation success. So this is, I think, an important part of the results because it shows what's possible with an agent that just sees and hears, enters an unmapped space, and needs to find the sounding object. And it's doing that without the benefit of instructions from the system saying, hey, you need to go to this delta X, delta Y position in the world, which is what the point goal agent would do. Instead, it's just finding it in a very natural way based on what it can sense directly. All right, so I've shown you then an example of navigation. I'm going to continue talking a bit more on navigation and show you how to bring in semantics for this problem. So in what preceded, I didn't really talk about what these objects were that we were finding. And they could be an arbitrary thing, a sound ringing, a phone ringing, or people singing, or anything else like this. However, in the model I showed you so far, and even in the platform simulations I showed you, there was a disconnect between the physical instances of these objects and the sounds they make. Furthermore, we had so far been assuming that the objects would always keep sounding, so we could just keep listening for them to go find them. So now what I want to show you, we've tried to relax both of those things and ask if the agent can navigate to a semantically meaningful sounding object, and to do so even when the object might stop sounding along the way. So the first thing we did was to enhance sound spaces to attach semantic sounds to objects. So there's an array of 21 different objects in these environments that have meaningful sounds we can place with them. For example, dishwashing sounds for the sink, or the alarm clock on the side table, or the toilet flushing. And so now we'll inject these sounds at the places where such objects exist so that the agent can start to learn not just how to follow a sound, but to understand the semantic meaning attached to that sound, such as what the object looks like and what rooms it might be found in. So we did this. I'm going to show you an example from sound spaces again, where first we'll hear a drawers closing, and then we'll hear a toilet flushing, and you'll see that corresponding in the simulation. So here again, the left is the ego view, and what you should pay attention to is the semantically meaningful. So you heard the drawers closing attached to this object from a distance. And there you would have heard the toilet flushing as it approached this bathroom. Okay, so now that's part of the simulation. These are physically meaningful, physically and semantically meaningful sounds placed at the object positions. And I won't say a lot about the approach, but the main advance we can make is to now learn this association between how objects look and how they sound, which, by the way, is an exciting research direction of its own. What's new here is being able to do this in an interactive way with agents that are moving in the environment to learn about this coupling of object sound and appearance. Furthermore, we introduced a long-term memory to handle the fact that these acoustic events might be short-lived. You might hear the toilet flush once, and now you're supposed to go find it. It's not that it's going to keep running and running and running. And so we developed a model to handle both of those things. And what it allows this agent to do now is to hear something in the environment. For example, suppose our robot is over here and it hears water dripping coming somewhere from the right. And then if it's learned well what water sounds suggest, like a sink or a shower, then it'll start proceeding in the environment in a meaningful way towards places that might contain a sink or shower based on the room context. Now perhaps the sound just stops, but with a memory that's long-term, the agent will be able to still proceed and, in this case, say, look towards the bathroom and expect that it's a sink that was heard, and then find that by sight. Okay, so this is a cartoon, but this is exactly the kind of behavior that we can get from an agent that we train, again, with some deep reinforcement learning, but now with enhanced memory models and the ability to learn this semantic connection. Here's an example of that agent at work. And here it's going to be finding a chest of drawers in this unmapped environment. So I should say on the right-hand side, you'll notice that there's dark gray and light gray. Dark gray is the full environment, but it's not observable to the agent. What it observes is the ego views on the left, and then carved out parts of this environment that you see starting to accumulate in light gray on the right. So here we go. Okay, so the sound has stopped, but the agent is still making its way to find that target object. Okay, so I have talked so far about finding these sounding objects in the environment, and now I want to introduce a layer of complexity on this problem that takes in a slightly different direction, where it's not just about finding out where the thing is that's making noise, but instead we want to hear better the thing that's making noise. So now there will be distracting sounds, there'll be something interesting and something less interesting we wish we could ignore, and our job will be to have an agent that can move intelligently to find a place where it can really hear well the thing it wants to hear well. For example, someone speaking in the house. And I want to contrast this problem setting that I'll dive into in just a second with what's happening in the literature for what you could call passive audiovisual source separation. So the source separation problem is to be able to take the audio you're hearing and optionally the video that you could see and be able to disentangle the different sources of sound so you could hear one at a time. And human speech is a great domain where you want to be able to do this. Now, there's been a lot of very exciting work in this space trying to tackle from video the source separation task. And what's cool is that the video will reveal extra cues that allow you to do it. Just think about being able to read the lips of the people to disentangle the voice of each one. However, this is passive, right? So there's a video, it's pre-recorded. You have no choice about the matter of where to be when you hear these sounds. And our idea is to consider this task of separation, but to do so in an active way with an embodied agent. So we call this active audiovisual source separation as a task. And the idea is to let the sound and vision guide the agent's motions so that it can better separate the latent monaural audio sound. Okay, so it's going to be in an environment, there's going to be overlapping sounds. It needs to pull out the one that's of interest and hear it well. So let me show you in this overview diagram what this task is about then. Suppose you had three sound sources, S1, a piano, S2, something happening at the table, and S3, some noise maybe at the sink. And suppose the agent cares about just one of those sounds. So maybe it's trying to listen to someone who's talking sitting at the bar by the sink, S3. Now it's going to receive the mixed binaural sounds from all three sound sources, no matter where it is in the room. But the idea is if it could move intelligently away from its starting position at the star towards a more useful position in which to listen to S3, then it will be able to disentangle and hear it better and just provide its estimate of the sounds corresponding to source 3. So in this example, maybe sitting at the star is very bad because you're hearing all these sounds at once coming from each direction, but moving over around this island in the kitchen is good because even if it's not exactly next to source 3, it's dampening the effects of S1 and S2 because of its physical placement. And this is the kind of behavior that we want the agent to learn. Right, so that is the problem statement. The approach that we've developed we call move to hear. And this again will make use of some deep reinforcement learning. But here a couple things are are different. So one, we're going to have two parts. We're going to have a model that's first trained to do audio source separation. So it knows how to take mixed audio and produce a target sound from it, from the binaural inputs. And we'll also have a memory that keeps track of those effects or those estimates over time. Now, as far as the action control or the motion control, before models I was showing you were optimizing to be rewarded for, and they're rewarded for getting to the target. Here, it's different, right? We don't want to be good at finding the target per se. We just want to be good at hearing it clearly. And so the reward for this agent will be based on the separation quality. So it's going to take as input the sights and sounds, but also the predictions from that separator network. And it's going to constantly try to refine the target audio. And the reward it's given then is, during training, how close to the correct target audio is that estimate. Okay, so short story of this slide is train an agent that knows how to move around well to separate sounds, because it's been trained to produce good disentangled sound estimates for a given target. And when I say given target, I mean when the agent comes in, it cares most about one category of sound. So maybe it's trying to find a certain human speaker and listen to them, or it's trying to listen to a certain musical instrument. So this is the move to hear approach, kind of in very short form. Let me show you an example of this agent in action. And when you look on the right, you'll see the agent as this arrow. It's going to start here, and then you'll see two red dots. Those are two competing sound sources. The target sound is actually where the agent begins, but it's going to need to move off of it in an intelligent way to hear it better.
It was so thoughtful.
I'm going to start this again. Okay, so the true sound it's listening for is this.
It was so thoughtful.
That's uncorrupted. That's what we want to be able to produce as output. And this is what an agent, however, hears at the beginning, the mixed sound.
Movie together.
As you can hear, there was a blend of three different sources going on there. So now finally, let me play the agent moving on the right, and you'll see that it places itself in a way to not be exactly at the target sound, but somewhere where the other sounds won't be as distracting.
It was so thoughtful. It was so thoughtful. It was so thoughtful.
So you can see as that clip kept playing, it was getting a bit cleaner and a bit cleaner. And that's because the agent has put itself somewhere where it can listen to that target sound well. Okay, and running this approach, move to hear, compared to a variety of baselines, these are results we get for being able to do quality audio source separation as measured using two standard metrics here, the SISDR and the STFT error. And the baselines that we're comparing to, let me describe briefly. So the top two, stand in place or rotate in place. This is, the passive agent, the agent that just hears what it gets to hear without having any control about where it should move. The rotate in place is at least smart enough to start rotating around to get different audio inputs. Other baselines are DOA. This is the direction of arrival. If we point our agent towards where it estimates the sound is coming from of the target, how well can it do? If we have an agent that moves randomly or moves randomly close by, those are the next two baselines. Or if we have a novelty agent, which is a standard exploration-based approach for a navigating agent to kind of get to know the space. Now, all of these are performing less well at this task than our agent move to hear that's trained to disentangle these target sounds. So these are encouraging results. Now, you'll also notice that on the right-hand side, if these are target sounds that we've never heard before, and not just clips we haven't heard before, but altogether new sounds we've never heard, then things get harder, although the advantage of having trained for this task remains. All right, now in the last part of my talk, I want to look into semantics combined with geometry and materials. So far I've talked about audiovisual navigation as a task we introduced, as well as this platform we've developed to support reproducible experiments and large-scale reinforcement learning models to be trained. And then I've talked about how to do this also for active source separation. Now we're going to look at how the sound in these places are quite useful for problems in mapping. Okay. And there's two things I'm going to show you here. The first one is about floor plan mapping. And the problem is this. Suppose you have a very short video in some unfamiliar 3D space. Can you infer the layout of the entire space? So when I say short, I mean, here's a camera that has walked through this environment. These cones are different camera positions and observed it visually. Now, we know that if we have ample visual observation of the space, certainly we can reconstruct a floor plan. So we could measure the full 3D environment, project down to a ground plane, and then realize where is the free space, where are the different walls. However, if you just have a small visual sample like this, there's a whole lot of the space that you just don't get to observe, and it's just not going to be possible to map it. Now, here's where audio comes in. If we can listen as we move around this space, then we have the advantage of being able to sort of see beyond the realm of the camera. Why is that? Well, there's two things. One, sound is bouncing around in a way that will reflect off of the further walls and let me know that further walls even exist out of view of the camera, or vice versa, that close walls might exist. So there's that effect. There's also the semantic sounds and their placement in the home. So for example, if this camera walks by a wall behind which there's a shower, but we hear the shower running, then that's a clue that first of all, there's free space there, and second of all, there's likely a bathroom there. Okay, so these are the exact two elements we want to capture, and to do it, what we'll cast is a problem of audiovisual floor plan prediction, and we'll ask our models to learn the floor plans in two ways. One, as a binary interior map saying where are the boundaries of each of these rooms, and second, as a semantic room label map that not only shows where these free spaces are, but also categorizes them into kitchen, bathroom, living room, etc. Now here, I'm not going to say a lot about the model for time, but we've basically trained in a supervised manner a model that can aggregate these audiovisual observations over time and predict the correct floor plan maps. And what's really powerful about paying attention to the audio is, again, that you can sort of see behind your agent now. You know, the microphone will catch sound from all over the environment and observe places that you don't observe visually, but still have some sense of their space. So, for example, look on the left-hand side of this 3D rendering of an environment. The orange cones are the camera placements over time. The cyan region is what you would get with the visual input. So if you projected down everything you observed there, that's the extent of the map you could make. The light green transparent region, on the other hand, is what we can predict using the audio. So you can see that we're really fleshing out a much greater part of the space. And that's also reflected in the top-down view on the right top here, where we're showing against the ground truth our estimates. So the true positives are green, the true negatives are black. You'd like this map to be perfectly green and black. That would mean we perfectly map the space. And then the errors are shown in red and blue. Now compare that to the best we could get with a state-of-the-art model for visual mapping that includes anticipation. So it also tries to anticipate parts of the space that weren't directly observed. And in short, you can see that the audio allows us to observe a much wider part of the space in the top map. Okay, so let me show you a video now of this agent collecting a short video and constantly updating these floor plan maps. And you'll see the same color coding I just showed you, where at the end, the cyan will show the visual output, and throughout the green will be what we're accumulating using the audio and vision together. So here's one example. Okay, so you could hear those semantically placed sounds in this Matterport environment. You could see that the agent limited to its site on the right in cyan has a more limited map, whereas the predicted interior in green encompasses a much larger area, and that's using the audiovisual sensing. And what that example showed is that we can do this using kind of incidental sounds. sounds in the environment, like a phone ringing over here, someone typing over there, someone knocking on the door, very busy household. Those kind of sounds were, by chance, but the agent can leverage them and learn from them to produce such a map. We've also studied a version of this where instead of whatever sounds happen to be in the environment, we pay attention to sounds and their reflections after issuing sounds from the agent. So I'm not displaying it here, but if the agent were to move step by step and emit a sound, then the reaction of the environment to those sounds can give also a sound about the geometry of the space. And in fact, when we learn with agent emitted sounds, we have an even easier time to do this mapping because we control the sound itself. Okay, I'll show you one more example of the floor plan. This again with environment sounds, and you're looking for how big and correct the map gets over time. Okay, so you could hear those bits and pieces of sound in the environment, allowing our agent to really get a reasonable view of much of the first floor of this house, just from a very short video. Okay, now the last piece of work I wanted to share with you kind of builds on this idea of agents that emit sounds to learn about the space. So especially with navigation, we were talking about a goal making a sound and then we would go find it. But as I just hinted at a moment ago, we can allow our agent to emit a sound to learn about the space. And so that's kind of the reverse observation. And why? Because when we receive the echoes back, it'll tell us something about the geometry. Okay, so the work I'm going to describe now is a feature learning approach that we call visual echoes. Okay, and I'm going to motivate it with an old movie. So here's a character who cannot see with his eyes, but he can see the environment by listening to the reaction of sounds in it. And so he's going to strike this gate and then hear the echoes and get a sense of the 3D shape of the space. Okay, so not using sight in this case, but able to sense the environment based on the echoes it hears. And of course, we know people can do this, and animals as well, kind of sensing by emitting sounds and hearing the results. So what we want to do with this idea of echolocation is actually to learn features that are visual. So we're going to learn an image representation in a self-supervised way using echolocation as the engine. And I'll explain all that in just a moment. And then we're going to show how it can benefit different spatial tasks like depth prediction, kind of like the video just suggested, surface normal estimation, and even again, visual navigation. Now, the key insight for our approach is to think of self-supervision coming not from a pile of static data, but from this agent interacting with the physical world. So in this case, acoustically interacting with the physical world by emitting sounds and listening for the results, all the while moving to observe in different positions in the environment. Okay, so this is the idea for visual echoes. Now, again, we turn back to sound spaces to generate data to allow us to train such a representation. So during training, what we're going to collect are views of RGB and depth, coupled with the echoes we would receive after emitting a sound at that position, at that camera position, at that orientation. And then we'll do the same thing for different orientations at the same position, right? So you could collect how the world looks in different cardinal directions, say, and then the corresponding echoes, which will be received differently depending on how this binaural microphone is oriented. Okay, so you can collect this kind of coupled data, and now we want to learn from this a representation that uses the audio to enhance our visual encoding. And so this is the idea of visual echoes, where we're going to learn the visual representation. The key self-supervised task that we set forth is to understand the congruence, meaning the agreement of the echoes and what we see, or their relative incongruence. So what that means is you have a model here that will be trained with a visual stream, and you have an audio stream. And during training, we'll supply those coupled views and audio spectrograms in different ways. During training, they may be aligned. So we might produce a view and these spectrograms that are consistent with the same view of the agent, or it'll be wrong. So it'll be an orientation of the sound in which the agent is turned right by 90 degrees or 180 degrees or so on. So that's how the training data is presented. And now the objective for learning this representation from both these modalities is to predict that orientation. Okay, so there's no semantic labels or human labels that are needed here. Rather, the agent is being asked to pull from the visual stream the features in a way that will allow it to understand if the geometry and spatial sensing from the sound is in agreement with what the agent sees or not. And furthermore, if it's not in agreement, what's the offset of orientation by which it's wrong? Okay, so this is a self-supervised task then. It's going to help us learn a good visual representation that captures things like the depth in the scene because of just that objective. Because to learn if these are aligned or not, we need to be able to pull from the visual stream the bits that say something about the geometry of the space in the same way the audio is going to be able to convey it. Okay. And in fact, this is an important part of the approach that what we're left with and what we want to leverage is the visual encoder. So during training, we have sound, we have echoes, we learn from them. But at test time, what we've really produced is a visual encoder that now we can use to apply to RGB images alone. Okay, so that's an important part about this approach. Train with audio, test with vision only, but leverage what you've learned about those modalities together while interacting with the environment to do better visual encoding. So as an example of that better encoding, first we look at depth prediction. So monocular depth prediction from a single image. And we're looking here at a standard data set, the NYU version 2 data set. These are real images. So that means even though we've trained this in our scanned environments with the Sound Spaces simulator, at test time, we're faced with a real photo from some totally different environment. The true depth maps are shown below in the second row. And then if you were to just train for monocular depth estimation from scratch, here are the estimates you get for those photos. And on the bottom, if you were to pre-train with the visual echoes encoding, you get cleaner estimates. Right? So what we've done is take this audio sensing during training, learn a representation that's better ready to expose the 3D shape or the 2.5D shape of this environment. And now it's prepared to better learn how to do this monocular depth estimation task. These are qualitative examples. Of course, we quantify just how good are they. And we compare not only the scratch model I just mentioned, but also to heavily supervised models. So a model that has the benefit of ImageNet pre-training, for example. And we can see that this task is getting enhanced with the pre-training that we do with the audio. Furthermore, it's not just depth prediction. We can do a similar kind of experiment with surface normals and also visual navigation, the task we started with in this talk today. And in each case, there's a strong benefit compared to training the visual representation from scratch for that task versus having pre-trained it with this visual echoes self-supervision. Okay. All right, so I'm going to end my talk here. What I've showed you today is all about spatial understanding from audiovisual sensing in 3D environments. The ideas I presented include the Sound Spaces platform, which again is publicly available and supported a lot of the experiments I showed you today. Then we looked at audiovisual navigation, and then we turned to look at source separation for agents that move to hear better, not just to find objects. And then in the tail end of this talk, I talked more about using the audio to do geometric sensing of the space, whether that was for the depth of the environment or a ground plane floor plan reconstruction. Now, the work I've shared today is with a lot of different collaborators, and I'm highlighting all the first authors here: Chanan, Unat, Sento, Sagnik, Ziad, and Rohan.